Hope my screen is visible to all. So in the last class, we just understood the concept of frequency division in depth. So today we were about to write the code for frequency division testing. So here, let me take a very simplest of the simplest code, and then we shall write the code for even this. Okay. So here, the example was somebody just made me the correction, so I'll correct it because yesterday we had some mistakes here. So let me correct it with a blue ink or black ink. I'll take. Okay. So the correction is, you just observe here in 2 raised to n is equal to f clock in divided by f naught. So 1 mega divided by 500 hertz. So here we forgot to divide this 1000 by 5. Directly I took 1000. I just it was a oversight, I can say. Okay. So now I'll let me take it. One second. Yeah. So let me take it here. So here if I divide, this is 5 ones, 5 twos. This is these zeros. I'll take it here. I think there is one more zero. So 2000. Fine. So it is actually 2000, not 1000. This is 2000. This is 2000. Now you can check in your calculator because there was an error, caused yesterday. So now let me check like what it will give. I have a calculator in front of me. So you also just go ahead with the calculation and check whether it is giving out the perfect answer or not. Log 2000 divided by log 2. So I'm getting it as 11. I'm getting it as 11. So that's a perfect answer here. I wrote the answer properly, but here I just missed out the intermediates. Okay. Because I had calculated it already, as I said, to save the time. So the same thing, we will just use it in writing code. So writing code just here, or let me type directly and show it in the Xilinx environment. So what we are doing is, so the only frequency division I'll explain. So here, normally, think that I'm implementing a simple counter, no reset, no nothing, only on the basis of clock. So what how does it behave? For example, 4-bit counter. So module, all those things you can write, inputs, outputs, all those things. So when I come to the body of the module, so I'll be having always at pause edge of clock being the input. Okay. So here begin and end, in between that we need to write. So here what we do is we just take one variable called count, which should be incremented at every pause edge of the clock. Okay. So here when we increment the count so many number of times, this count should be declared in the module. So here it should be declared. How? Reg count equal to, you need to initialize it and then semicolon. Here you need to decide how many bits you need. So just in the previous slide, we decided that n should be equivalent to 11. So I use 10 down to 0. So 10 down to 0 is including 0. I'll be having total 11 bits. Or on safer side, you can even declare it as 11 down to 0. It's okay. So here it's 11 bits. 11 tick B or D, I can say. Let me erase it. Let me write D, because if I write B 11 times, I need to go on writing 0. So if I write D in decimal, it is just 0. So this register count has been declared. Now what I do is I define new clock. So new clock is count of 10. That's it. The 10th bit of, or the most significant bit of this count, I am assigning it to the new clock. Now new clock is not defined, hence define that also. The next line of this reg new clock is a single bit, because clock is a single bit, new clock. So this completes your frequency division. Now what we do is we take the further code as it is, always at pause edge of Pause edge of what? Pause edge of new clock. I'm taking new clock now. I'm taking new clock. Begin and go on writing all the things. End this always block and end module. So this new clock is divided, frequency divided clock. For example, if this clock is of frequency 1 megahertz, which comes to be 1 microsecond. 1 divided by mega means 1 microsecond, which is too fast. Here after frequency division, the output will be new clock. So whose frequency is 500 hertz, which will give you t is equal to 1 by 500 will give you 1 by 5 is 2.002 if I'm not wrong. Okay, so just let me check. Yeah, or else let me write it as 2 into 10 raised to minus 3, which is 2 milliseconds. So I want to divide this frequency by so many number of times. So hence to do this, I need n is equal to 11. So n minus 1, this is assigned here. So this new clock will be of period 2 milliseconds. This clock will be of period 1 microsecond. That's the difference. So this is frequency division for you. Now we will take this in the Xilinx environment and check. Okay. So here, let me close the project. Open project. So here I'll take unit 3 behavioral. Okay. So there are a lot of codes that we have taken in unit 3 that shows that itself shows how much importance this chapter is having. Okay, it's too much important. So here what we are doing is I'll take the one which we have already done. So let me just take ring counter. Okay, so ring counter, I'll take this code and I'll introduce a frequency division here. So how to introduce a frequency division? So here what I do is, see, this is, I'll just maximize it, just concentrate here. So I'll make it very easy for you. This is a body of the module. Okay, I have written here, this is case statement. So I'm neatly arranging it. So this is case statement, begin and end. Begin and end. This is end module. Okay. So here what we are doing is I'm writing a frequency division. Frequency division code. Frequency division code I'm writing. So for that what I need? Always, I'll write it here. Always at pause edge of clock. So I take the reference of pause edge of the clock. Okay. Then begin. Same thing I'm copying. What I just now shown you in the previous slide. So begin. So here I define a count variable so that I want to increment it at every pause edge. And then I'll assign it to new clock with the most significant bit of that count. So if I define the count with 11 bits, then the most significant bit is 10, semicolon. This is end. Fine. This is end. This is a main code. This is a main code. This is a frequency division code. Now I have used count and new clock as a new variables declared. Let me declare those things. So let me declare here reg. So count is of 10 down to 0. 10 down to 0. So count, which is equal to 11 bit decimal 0. This is the initialization. The new clock, I need to declare it as reg. New clock is reg. Let me initialize this. This is a single bit, so hence one tick, B or D, both mean same, so 0. So this is the initialization, and here we have a piece of code, and then end. So in the new code, before this, the clock was varying at the given clock pair. Now I want to decrease its speed. So what I do is I take the reference of the new clock. So I write it as new clock here. I write it as new clock here. So you get it as, so this is the code. That's it. What new extra in extra we did? Only this much. We declared count of the required number of bits, and we declared new clock to assign have the new clock frequency divided clock, and then always at pause edge of the clock take the reference of the clock, go on incrementing the counter. That's it. So new clock to be assigned with a maximum or the most significant bit, because that is how we calculated in the previous slide. Okay, and the code remains same, only changes take the reference of pause edge of new clock now, so that it varies, it changes the state slowly because the frequency is decreased. Frequency is decreased means delay is increased. Now let me save it. This is what, ring counter, right? Ring counter. Let me synthesize it. I hope there are no doubts up till now.
Sir,
Yes.
it should be small p, no, sir, in first
Yes,
program.
yes, yes, yes. That's it. Exactly right. Thanks for pointing it. I have already synthesized it. Let me check. Let me check what happens. Okay. So very good. So it's getting synthesized. So it is telling synthesis failed. Let me check the error. So line 22 or error nearer something it is telling. It means in the module there is some errors. The module is ignored because of some errors. So 22 it is telling, see, sometimes it creates a lot of difficulty. It is telling there is some error here. So to just identify it, somewhere if you commit such mistakes, keyword writing mistake, then such problems happens. So it's a rightly pointed, see, capital P, and it is highlighted with black font, means it is treating it as a variable or identifier. Now as soon as I change it to small p, then it is pause edge, it is a keyword. So I'll save it and run it again. Okay. So in Xilinx, this is one helpful thing for us. Comments with the different font, green font, keywords with blue color font. Like that, it will highlight us. And system tasks with pink color, not, yeah, not pink color, orange color. There is again an error. Let me check what is the error. So same thing, error, syntax error near double quotes. I think it was the problem we faced in the earlier class. Um, there was, I think we took this ring 123. Let me just take the outputs and inputs from there, because I said because of ASCII code it was creating some problem. Okay, so here open bracket output queue is declared. Then this output I have also I should also declare it as 3220 queue with register also. I just copied it in the last class. See, I had took three ring counters. I took the wrong one because that was showing the error while ASCII conversion. We'll try it once again here. We will try it once again here. If it works, fine, or else we will write the code by ourselves. Okay, don't worry. So let us check. Synthesize it. So rarely, I repeat once again why such error comes, because even though you don't find any scriptical error, why it shows, because Xilinx does not identify certain font sizes or font styles which are there in your Word or PPT. So that's why this problem comes. Okay. So let us not worry. So we shall have, we will take sequence counter itself. Here I'll not change anything. I'll just check syntax it. If it is working, I'll copy that frequency division code here itself. Okay. Because ASCII code conversion has worked properly here. That's why. So normally we don't copy paste, right? We just here why I'm copy pasting, because in order to save the time, if I go on writing all the codes, then it takes a lot of time. So I'm just copying it. See here, go to sequence counter. So here, is a frequency count. This one is count initialization, register and initialization, and then this clock. I'll take the new reference of this new clock as new clock here. That's it. Okay, so here ASCII code conversion problem was not encountered, so I took it. In ring counter also it works, so it is not like I have why I've shifted here. I forgot like which ring counter I took, ring 1 2 3 or ring count, which ring counter. You can test it. It will definitely work with any of the code. Make sure that you are not copying it directly. 90% of the time copying also will work. ASCII conversion will be successful in Xilinx, but sometimes it will create problem like as I have shown you. Okay, so here see, you can see that check syntax is done. I did not change anything, so it is as same as earlier, but it worked. So this is not the problem from your end. Okay, so simulation sequence counter is the one which we took. Now here what we need to observe is in the code in the simulation that I shown in the previous class. So there I took the reference of clock. Here I'm taking the reference of new clock, which is divided by 11 times, or I can say from 1 megahertz to, so 1 megahertz to, it is changed to 1 milliseconds. Okay, so here I don't restart it. So here it is microseconds. Let me keep the clock, the original clock, with 500. What is that? 1 megahertz. What is 1 megahertz? 1 megahertz means 1 divided by 1 mega is 1 micro. So my clock period should be 1 microsecond. So I'm keeping it as 1 microsecond. My clock period is 1 microsecond. So what I did, I think I have to force clock leading at 0 1, period is 1 microsecond. So this is how you need to keep. Click on OK. So clock is set now. Directly Q will come. So on the basis of new clock, your Q actually operates. That is what we check. So here for readability, I changed the clock to reduce to unsigned decimal. Okay. So I take this new clock just beneath the clock, and this count, let it be here. Okay. So let me run it. Zoom to fit. So you can see here the clock has got its first positive edge. Count is incrementing. Why count is incrementing? Because count is incrementing with a reference of the original clock itself. But what about new clock? So with new clock, so it has to, this clock is being divided 11 times if its frequency, if I take. But if I take its delay, the delay has been increased. So this delay is 1 microseconds period. Yeah, the period of the new clock will be 1 milliseconds, because 500 hertz, if I take its reciprocal, 1 divided by 500 hertz, 1 divided by 500 hertz, right? What I did, but 2 milliseconds, right? 2 milliseconds. So let us check. I just go on running it. See, I go on running it. So your new clock is not producing single positive edge up till now. So I run it so many number of times. Means the delay is increased too much, too much. So what I do is I just rather than all the time clicking it, so I run it for directly 100 microseconds. Okay, still new clock is not there. Still new clock is not there. Okay, so now new clock appeared. You can see here. So here new clock has appeared. You can see here new clock is appeared. Let me, you can see here, as soon as the new clock's pause edges appeared, your Q has transited to 1. See, initially this Q was incrementing, or it was starting the counting session. So at pause edge of the clock itself, now you see here pause edge of the clock, so many pause edge of the clock, still it has not you know opened it, or I mean have the rising edge. So after certain amount of delay itself, it has got positive edge. See, I'll run it one more time. I'll run it again. Zoom to fit. I'll run it again. Zoom to fit. So still one period is not yet over. Okay, run it again. Now it has got produced. So you can see here, I just run it one more time. You can see here, you can see here. What is the time here? It is 2048 microsecond. So 2048 microsecond means I can say it as 2 milliseconds. This dot, if I shift it here, I can say it as 2 milliseconds, right? What is the calculation we got here? 2 milliseconds. So if I take the reciprocal 1 divided by 2 milliseconds, then what do I get? 500 hertz. So I shown that my concept is working fine. Now the question might be like, so here if I just zoom it, you can see here, 2 milliseconds comes exactly at this point, right? But the clock period has been extended for 48 milliseconds in extra. 40, not 40, yeah, 48 milliseconds in extra. Why that 48 milliseconds in extra we got? Because that I'll tell it here. So here in previous slide, we analyzed that n is equal to 11. But what is the exact value? Exact value is 10.96. So this difference, 11 minus precision, I can say. What is the precision? 11 minus 10.96. So that is that you get it as 0.96, 0.96 or 0.096, 0.096 it is. Uh, one second. See, sometimes we commit mistake in easier things. Complicated things will do it. So that's why I don't mind calculating in this manner. Okay. So 0.004, 0.04, 0.04. So this is the precision. Okay. With that precision, I'm getting the here. With 0.04 is a precision. Means 0.04 into 100. So 0.04 into 100 is I can say 4%, right? Yeah, 4%. So 4% error may be there. 4% error may be there, because of which you get this 48 millisecond in extra. So that error is introduced because we have rounded off there, approximated there. Now we shall run it. Okay, I'll run it in the place of the 1000. Let me run it in the 2000 microseconds at a time, because at 2000 microseconds I'm getting a clock. So just here. So this is new clock. Okay, the old clock is toggling so many number of times. My interest is on only new clock. See, I'll run it now. See here, count as sequence. It is a sequence counter. So 0, 1, 5, 7, 9, 12, right? So it is going in terms of milliseconds. In the beginning, the clock's frequency was set to only microseconds, that is megahertz. Now it is 2 millisecond is one period of the clock. You can see here, 2 millisecond is one period of the clock. So this is how the frequency division works. If you have any doubts, please come up in the chat box. I'll just take out the doubts now itself, because frequency division is a very important concept. Please come up in the chat box. Any doubts? Please come up in the chat box. Yes, any doubts you have? No. Did you understand, all of you, did you understand the frequency division? Because it is a very important concept, that's why I'm stressing more upon it. Quick, 48 students, at least I need 20 comments, because it's a very, I had just told you in the previous class. It may sound funny. Very, very, very important. There is an intention before writing it. Okay. wait till 65. Yes, okay. I got at least 20 comments. Fine. So it means there are no doubts. Let me proceed with the assumption that uh, okay, next what shall I take? Okay, let it be. So few more example I can show, but okay, I think this is sufficient. This is sufficient. So we shall directly go to the next one. Okay, let me present my screen again. So next topic is the again the new topic for the consideration. New topic being, so here loop statements. Loop statement is a new topic. So up till now, what we covered is we understood conditional statements. We also understood case statement and frequency division in between, because a lot of counters we designed. So these frequency division can be used in that counters. So loop statements. Four loop statements that we have in Verilog are while loop, for loop, repeat, forever. So while loop, the keyword while is used to specify this loop. The while loop executes until the while expression becomes false. Increment, so it means this is similar to your C program. So that's why I'm just, I know I can write it here. Similar to C program. Okay. Keyword while is used. While loop executes when while expression becomes false. While loop executes until the while expression becomes false. Let us take an example. Okay. So this example is increment count from 0 to 127. Increment count from 0 to 127. Exit at count 128 and display the count variable. So here again it is a counter, but I'm using loop statements. So before I proceed with the loop statement, let me generalize, or let me tell you some important points. So points to remember, I can say points to remember. So first is loop statements. Okay, normally used. Loop statements are, this is not from the textbook, this is from my experience. Okay, loop statements are normally or normally used in stimulus blocks. Stimulus blocks. Next, second important point. It is recommended, not a strict rules, but it is recommended to to avoid loop statements, loop statements in the design block. I hope you understand what's a design block. The design block. Why so? Why it is used in only in stimulus block? The stimulus block is just for testing the input cases and giving the input cases test vectors and checking the output functionality of the design block. What is the design block? Design block is actually the core, right? Design block is actually the core for us. This design block should not, normally, usually, it is recommended to avoid these loop statements. Why? Because see, think that you have used a loop statement. Like count is incrementing. So count is incrementing means count is equal to count plus 1, right? So this count plus 1 will be having some hardware. I'm just taking simple example. If you put it in a loop, while loop until some condition is satisfied, then your hardware should replicate this hardware, I mean this prototype of the hardware, or else I can say soft core of the hardware. This has to be repeatedly appearing in your mapping or synthesis also. So this, if it repeatedly appears, then your hardware consumption becomes too high. When your hardware consumption becomes too high, then what happens? Then you run out of the space to fit in your hardware. So this is not called as optimized design, unoptimized design. Maybe it synthesizes if it is within the limit, but it is unoptimized design. Hence, always avoid using loop statements in the design block. Okay. So now come to this. Then why it is used? I said it is for stimulus block. Majorly it is for stimulus block. Somewhere in some places you can definitely use this loop statements if you know that it will not affect the optimization or the design. So integer count is a variable of a focus which is incremented from 0 to 127. Initial begin count is equal to 0 while count is less than 128. Begin, why 128? Because we have been given the exit condition. So what is the exit condition? Once the count reaches 128, come out of it, come out of the loop or stop the counter counting. So you need to display the count. So they have given that display the count means it is displayed only in the console. So this dollar symbol display system task is used only for simulation purpose. Okay. So dollar symbol display count is equal to percentage d count. So this is a dollar symbol d display. We have already discussed it. So percentage d is your count. So count, as count goes on incrementing, so it will go on displaying. So initially count start with 0. So 0 is displayed first, then followed by count equal to count plus 1. So count increments, so it goes on incrementing. Okay. So let us have this code. Let me check if you have any other code. So we have a few more codes. Let me just analyze those things and then we will take it in the Xilinx platform. Okay. So here register flag is a 16-bit vector. Integer I means it is 32-bit system dependent. Majorly it is 13-bit, 32-bit. Reg count continue, it is single bit. So this is command line. Okay. Or if I put it like this, it is a command line, 1 bit. Then initial begin, there are two things initialized. One is flag is 16 bits, so 16 times 16 bits you need to take it here. And this you can also write it as without having these things, but in order to have a proper readability, Verilog allows you to introduce underscores in between the numbers for improving the readability. This, while 16-bit means it will come to the compiler gets to know that this is a number what it is reading. So when it encounters underscore, then that will be ignored. Only numbers are taken into the consideration. But other than underscore, if you use hyphen and all, it will throw some error. Okay. So you can use underscore for readability. So here you can see that the one of the bit is made high, like 15, 14, 13th bit, 13, index 13. That bit is made high. So I is equal to 0. Continue equal to 1. It has been specified as 1. So let us see why is that what is the purpose of doing it. Okay. So while I less than 16. So here the question is, this is a question, find the first bit with a value 1 in flag. Means think that you have a 4-bit number, 4-bit number like this. If I ask you to find the index or where the first bit 1 appears. So it starts from here. It will check if it is 1. It will check, think that it is q. It will check if it is q is equal to 1 or q of n, or this n is varying from 0 to maximum. So this is not 1, so it will go to the next one now. This is also not 1, then it will go to the next one. So this, let me call it as I. Okay. So I equal to 0, there is no 1. I equal to 1, there is no 1. I equal to 2, there is 1. Means q of I when I is equal to 2 is 1, or else I can say simply q of 2 is 1. So this index should be displayed. Okay, this index should be displayed. That's out is the meaning. Now here, if I analyze, here the flag is the 16-bit variable. Index comes over here. So when at what point of I question mark I'll put it here, one has appeared, first one has appeared. So it starts checking from here. This is I, okay, this is I. It is 0 1 2 3, no one has appeared. 4 5 6 7, no one has appeared. 8 9 10 11 12, till here no one has appeared. At 13, whenever it encounters 13, so it will display it as 1. So question mark is replaced with 13, or else I can say flag of 13 is equal to 1. Okay, so flag of 13 is equal to 1. So with this, we designed the logic for encaching it. So now what we do is we proceed with the algorithmic design. So here what we are doing is continue is set as 1. Let us see why it is. While I is less than 16 means I go on incrementing I. So at 16 it should stop, because from it has got less than 60 means at 15. 15 is the last one. It has to stop. That's a maximum range, I can say. I'm specifying the maximum range. Okay, begin. If flag of I, that's what I'm telling. If flag of I is begin. So I'm checking the if condition. If flag of I, if I just only write this, this is as good as writing flag of I is equal to 1. If it is 1, then what should happen? Display encountered a true bit. True bit means 1 bit at element percentage d. Percentage d is I. So this, now once you encounter the flag bit to be 1, stop it. To stop it, I use a command called continue equal to 0, means don't continue, end it. This is if statement. Then I increment I is equal to I plus 1. Excuse. So I is equal to 1. Now till now, I'll go with one by one. Let us start with I equal to 0. So flag of 0. Flag of 0 is 0. Flag of 0 is 0 means if statement will not execute, directly comes at after the end. After the end, what is there? I is equal to I plus 1. I is 0 now. 0 plus 1 is 1. So after 1, it will check while. So 1 is within the range, and continuous still, it has not encountered, means continuous still set as 1. So both conditions satisfied. So it will come here. So now I is 1. Flag of 1 is equal to 1. That will check. So it is still 0. It will not enter the loop. So it will come over here. Now I value is 1. So it will, when 1 plus 1 is there, it will become 2. Increments to 2. So 2 is within the range. Continuous still set to 1 itself. So it will execute. Like that, it will continue till 12. So once 12 is done, 13 comes. When 13 comes, 13 is still within the range, continuous still 1. Flag of 13 is 1, so definitely it is 1. So flag of 13 is 1. Now this statement gets executed. Encountered a true bit at the element number percentage d. Percentage d is I means 13. So 13 will be displayed. So continue is set to 0. So when it is, once it's set is 0, it will come out of the loop. I is equal to, it I becomes 14 because it has not yet reached the maximum range. So with I 14, I proceed here. I is equal to 14 less than 16, it is true, but continuous becomes 0, so it is false, and it is a AND operation, hence totally you will get it as false. So when it is false, while will terminate and it will take you to the end statements. After the end, you have end of the always initial block and your process terminates. So this is the first bit finding with a value 1 in a flag. Okay, so if you have like this 0 0 1 0 0 1 0 0, so if I ask you to find the first bit of the one, means I equal to 0, it is this. I equal to 1, I equal to 2. At I equal to 2 itself, your first bit comes as 1. So no need to proceed further. There is one more one. I am not interested in it because we have been asked to only find the first bit with value 1. This is the first bit with value 1. So I found it. I don't proceed here. No need to require. So hence, once you come at this position, I goes on incrementing because of that automation or algorithm. So you have to make this continue equal to 0. That's it. So by doing this, your process stops there itself. Okay. So this is the flow. Next is for loop. Before that, we will take this code into the uh, Xilinx environment. So give me a second. I just check if I have. Oh, give me a second. Okay. One more minute. I'm just finding if I have already written the code and kept it ready. So I'm just searching it. If I'm having it, then my work will be reduced, and today I can complete that while part completely. Okay. Yes, I got it. Okay. Let me share the screen. So I need 2 more minutes or 10 more minutes to show it. Hope my screen is visible to all of you. Yeah, it's visible. So I'll take the first example. The module name is count underscore mod. This is just for simulation. It's counting, right? So count it till 128. So that is what I'm testing now. So implementation, it's not implementation actually, simulation. Right click, new source, Verilog module or Verilog text fixture. Anything you can take. I take a Verilog module because I'm not attaching any design module. So here, what is the name? Name is count underscore mod. Count underscore mod. Next, next, finish. So I'll just copy it. So I copied it. You can see here. I'll zoom it and show. So there is no difference. There I had started from integer count and so, and it is creating some problem, and I copy from PPTs directly to here. That's why I've saved it in the notepad so that formatting should not be altered. So here same thing, count is 0, count less than 128, display count value, and count should be incremented after every 5 time units. So this is a thing that we have done given. So now we'll see how it works. So here there is no clock, nothing. So it's just simply we will just run it and check. So count underscore mod, run it. Okay. So this is a while loop. Fine. Until the condition is satisfied, it will run. Once the condition is not satisfied, it will come out of the loop. Executes the loop till count is 127. That's the meaning. I'll change the radix to unsigned decimal. See 1, 2, 3, 4. It goes on continuing up till 97. So I'll zoom it further. Still it is counting at 127. It will stop counting, means 128 it will reach, but that's it. After that it will come out of the loop. That's it. Okay. So this is a while loop demonstration with our first example. Now the second example is very important example. See here I am taking a directive, or I can say compiler directive. So here find true bit, find underscore true bit is a code name. So let me just have this here. Right click, new source, Verilog module, find underscore true underscore bit, first to true bit. Okay, find underscore first true bit is the first you're finding. So I'll just copy that code. Already I have explained it in detail, so let me directly have and show you what in extra I have written to that particular thing. I started from here, reg flag integer I, reg continue means I've just written continue, cont, that's it. Flag is initialized, I is initialized, count is set to true. You can set it to 1. It does not create any problem. I'm just wanted to give the demonstration on tick define also. That's why I'm taking like this. Continue is equal to 1, continue is equal to 0. That's it. No change at all. So when I encounter this backtick true, it will read here tick define. I have defined this true as a 1. So wherever true comes, it will replace it with 1. Wherever false comes, again compiler is directed that whenever false comes, it should be replaced with 0. So it will replace it with 0. 0. So this rest everything is same. This is 1, this is 0. That's it. No change at all. Now I'll save it, and it is, what is the name given for it? Find a true bit, right? Here's a find a true bit. I'll just run it, and we'll see my answer should be this is 13, index 13. That is what we need to get. Okay, let us check. Yeah, zoom to fit. Flag is as it is. I'll change it to the radix unsigned decimal. So you can see here. At 14th it is telling. So let me check. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 it is actually. Index is starting from 1 here. So we are actually 30, 14. It should not be 14. Let me check where we have gone wrong. No, no, no. It's not 14. Uh, I should be displayed. Yeah, here it is displaying in the console. Sorry, we have displayed in the console, right? Let me check in the console here itself. Here it is. In the console, it is displayed 13. So after 13, I just explained you also that. So once 13 is encountered, it is true. This is also true. Flag of 13, it will check it is to be 1. So it will display 13. But after that, it will come out of the if loop. And while loop is not yet terminated. It will increment I once. It will increment I once first. So 13 becomes 14. So hence you are getting 14 here. So it is not a mistake. It is intentional. I said it and I just forgot to write it here. So this is 14, but at 13 itself, I got it. So that is what is displayed here. You can see here 13 is displayed here. Okay. You can store it in some variable and you can also display it here. That is also okay. Now what I do is I just change this. I insert 1 here. If I insert 1 here, what should be the index value where the first bit with 1 value has come? Start from 0. 0, 1, 2, 3. At 3, I should get it. Let me run it and check if I'm getting 3 displayed. And I should be 4, but displaying should be 3. That is happening or not, we will check it. Okay. So just wait a while. Just wait a while. You can see here what is displayed here? 3. It is 3 which is displaying. So here just I'll show it with a radix 4. So means one less than that would have been displayed. 3 is would have been displayed. This is the first bit. You have two number of ones, two bits with value 1, but the first bit is declared is used for displaying the index. That's it. So this is about the while loop. If you have any doubts, please come up in the chat box. And that's it for today.